Hello everyone and welcome to my presentation on fine-tuning LLM for abstractive news summarization. So this project focuses on generating concise and meaningful summaries from long news articles while maintaining factual accuracy and fluency. So the goal is to show smaller language models when fine-tuned efficiently can perform nearly on par with large state-of-art systems such as BART or PEGASUS. So our workflow of this project is we begin by preparing and cleaning the data set, which is the real data set from the CNN articles, then followed by tokenization, formatting, and fine-tuning the LLM, which is the model is TinyLlama 1.1 billion parameter using LoRA and quantization. So we'll go one by one, and at the end we'll give the demo of how everything works. So the first is the environmental setup where we have to have the Python installed and we can use any kind of IDEs or environments, which is Google Colab, Kaggle, or any kind of environments. Specifically, if you have GPU, that would be sufficient because this is a NLP model where you need to train a lot and it takes some time to train. So we have to have the modules installed, which is like torch transformers, ray tune. So these are the important things which we need to install before going forward. So the detailed installation documents and environment setups is given by me with the README file, so you can use that one too. So going forward, the data set which I had taken is from the CNN, where there are news articles the real world news articles, which is ranging from 2015 to 2021. It has like 287,000 of training data and 11,000 data validation and 13,000 um, tested. So we'll go to the dataset, which is the present in the Hugging Face. So this data is grabbed from the another author, which is given by Ramesh Nalapati, where there's a paper which describes how he scraped and everything. So I'm using this dataset for my fine-tuning the LLM with Tiny Llama model. So going forward, we'll tokenize this data set. We'll train, first we'll pre-process the data set, where in pre-processing we'll have a pre-process function which do tokenizations and mapping the prompts with patterns and storing it in a separate test set, validation set, and training set. So next step would be model selection, as I already mentioned. So which is the TinyLlama 1.1B billion parameter. It has like 1.1 billion parameters and instruction tuned decoder only transformer. It offers excellent balance between efficiency and expressiveness. So to make it fine tuning more friendly, I applied a 4-bit quantization and bits and bytes library. So this step compresses the model weights and reduces VRAM by 70% by maintaining numerical stability. So after that, the fine tuning itself employed LoRA. So instead of updating all weights, LoRA inserts small trainable metrics into the query and value projection of layers. So I'll give my configuration here. So the after configuration, I did a rate tuning for hyperparameters. So the search space which I used for the rate tuning are the learning rate, gradient accumulation steps, and weight decay. So I have these three as the weights, and I passed this to the training function which I have here. So this training function trains the model based on the search space which I mentioned, and that gives the rogue score, loss, and along with the other parameters which I used to do. So once everything is done and everything is trained, so this will go on for a while and we'll be getting the hyperparameter tuned results where the results will have the data frame where it has gradient accumulation, learning rate, weight, decay, along with three rogue values and evaluation loss. So the best configuration evaluation loss is the uh, learning rate 2.5 and gradient accumulation 16, and the best configuration for rogue L or rogue is the learning rate 1.01, and gradient accumulation 4. So we are gonna use this one because our evaluation matrix is based on the ROGUE score. So as you can see, the ROGUE score is determined from each and every trial. So there are 4 trials, and we used the ROGUE score to get all these things. Next is after getting the best model from the ROGUE score, we are gonna use that model to or the configuration to train the best model and compare that one with the baseline. So while compare training with the best model, so we'll have the entire test set validation set evaluated based on the ROGUE score, and the results are stored in the data frame here. So this is the configuration for the baseline model. So we'll compare our best model with a baseline model here, where the results are stored in a separate CSV file where we can get all these values. So on the next step, we are going to visualize how it varies and how it is different from the state of art composition. So the state of art, we have 5 different graphs here. So to get the values, the ROGUE score, which is like a base versus optimized, you can see the best ROGUE score is 0.279 and the baseline score is 0.268. So you have a considerable increase in the ROGUE score, and also this is the ROGUE 2 score and ROGUE L score. So ROGUE L score is like a F1 score where we use this to determine, but for our model, we are going to go for the ROGUE 1 score. So you can see it's a considerable increase in the ROGUE score because we have optimized it and we have fine-tuned it based on our model. So then the ROGUE score is compared with the state of art, which is when compared to Pegasus and BART-Large. So our best model gives like a 2.79, whereas the best Pegasus model, which has a value of 0.34. So as we can see, like it's around 80% of the uh, data, like 80% of the accuracy, like our relative performance, it does give for this ROGUE score. And we can have the performance gap as well. So when benchmark against the larger models, the tiny llama model reached like 80% of the BART language and 78% of the Pegasus performance. So which is an impressive outcome considering the drastic difference in the parameter size. So the Pegasus model will have billions of data, and our model llama has like a 1.1 billion parameters of our model. So when we compare this, this is a very good thing. The evaluation loss remain consistently low, and rogue improvements also demonstrate enhanced fluency and content preservation. So beyond quantitative metrics, the qualitative evaluation shows how effectively the model captures the key context of an article. So the loss and the log curves, row curves are smooth convergence with no instability. And for the error analysis, we are just getting the data and running for the few uh, text articles where it has performed very good on some, and it doesn't give very good generation text for the other one. So we have identified the pattern. So that pattern, which is relatively based on the Rogue One score, where you need to have the very good score in order to get the best text generation or the summarization of the text. So the next one would be like a sample prediction. So I'm gonna use this model to sample, sorry, so generate a text based on my user input. So right now I have given article from the CNN, which is like technology and Apple announced its latest quarterly. So I have copied and pasted everything here. And when I try to generate the summary from my model, so it correctly summarizes and then it gives the proper highlight of this news article. So as you can see, it has like Apple Incorporated, which use the short form as well, and all the values here, which is like 123.9 billion and iPhone 14. So everything seems proper here. So in conclusion, the project successfully demonstrated that our model, which is TinyLlama, when fine-tuned using LoRa and 4-bit quantization, can perform at high quality and efficiency. It achieves around 77 to 80% of the state-of-art performance while operating within a modest hardware constraints. So, in the future work, the approach could be extended by incorporating reinforcement learning for human feedback, refining beam search, can do anything. So, overall, the project highlights that a small, well-optimized model can pave the way for accessible and cost-effective summarization systems. Thank you for watching this demonstration.